All right, we're going to talk about 13.2 today, forces of attraction. Forces of attraction. There's a joke in there somewhere, but can't think of it right now. So if all particles of matter at room temperature have the same average kinetic energy, why are some materials gases while others are liquids or solids? Right? Piece of metal is solid at room temperature, but water is liquid at room temperature. They're the same temperature, so why is that? Why are they different states of matter, yet they have the same average kinetic energy, right? They're both room temperature. What it comes down to is that there are forces between molecules that we need to consider. Okay? And something confusing about this that it points out, the term molecular can refer to atoms, ions, or molecules. So it's a little confusing, but we're not just talking about only molecules, because remember, molecules are covalent things, but the term molecular can refer to molecules, ions, and atoms. So intramolecular forces do not account for all attractions between particles. There are forces of attraction called intermolecular forces. This is intra. Okay. These forces do not account for all attractions between particles. There are other forces called intermolecular forces. Okay? So this is intra. This is intra, stuff we've already learned. Now we're going to learn about intermolecular forces. Okay? The three intermolecular forces that will be discussed through this section are dispersion forces, dipole-dipole forces, and hydrogen bonds. We have not learned about those. We have learned about these intramolecular forces, but not about the intermolecular forces. Although some intermolecular forces are stronger than others, it's important to note that all of the ones we will learn today are weaker than these three that we learned a long time ago. So remember about ionic and covalent bonding. Those are way stronger than the stuff we're going to learn about today. These are still the strongest things, but there are other forces that we need to take into account if we're considering why metal and water are different states of matter at room temperature. Okay, let's look up dispersion forces. The force of attraction between two equally electronegative particles is called dispersion forces. Dispersion forces are weak forces that result from temporary shifts in the density of the electron clouds. So remember that around the nucleus, there's these electrons in the electron clouds. And what dispersion forces are every once in a while, all the electrons happen to be on this side of the cloud. This is a simplification, but all the electrons are on this side of the cloud. So what happens is this side's just a little bit more positive. And since this is just a little bit more positive, it kind of just a little bit attracts the negative a little bit more over here. So just temporarily, they exist as a dipole, or they exist as positive and negative. This does not happen for very long, but it does happen. And you guys know that opposites attract. So temporarily, there's a little bit of attraction between these molecules. Okay? It's not a covalent bond. It's not an ionic bond. There's just a little bit of push towards each other. But this is temporary. And due to the fact that these are temporary, these are the weakest types of these forces. Okay? Of the intermolecular forces that we're talking about, the ones between particles like this, these are the weakest. They do technically exist between all particles, but they only make like a meaningful difference. That might not be said. They're only important, I guess, when there's no other forces of attraction between two particles. Okay? We see here dispersion forces are the dominant force of attraction between identical nonpolar molecules. For example, fluorine, chlorine, bromine, and iodine exist as diatomic molecules. Okay, but remember that the nonvalence electrons increase from fluorine to chlorine to bromine if we look at a periodic table. So fluorine's up here, chlorine, bromine, and iodine. Recall that the number of non-valence electrons increases as we go down from here to here. Okay? Because the larger halogen molecules down here have more electrons in their interior, there can be a greater difference between the positive and negative regions of their temporary dipoles, and thus, down here, there are stronger dispersion forces than there are up here. Because you can think of it as a stronger cloud, so the attraction can be temporarily stronger than up here. This difference explains why these guys are always gases, this is a liquid, and that's a solid at room temperature. Because of these tiny forces that just get added up and added up over time. But it's all temporary. It's just when you add them up with so many particles, you get an actual result of this dispersion force. Okay? So the more atoms there are, the stronger the cloud. It's still temporary, but that's why the bigger halogens are solid or liquid, and the lighter halogens are gases, because they do not have a strong attraction to each other. They can just float away. So those are temporary, and those are weak. Those are the dispersion forces. Now let's look at the dipole-dipole forces. These are when molecules that are very clearly positive and negative. Okay? So here we can clearly see this is a negative side and this is a positive side. That doesn't really change. This is always positive, or this is always negative. The green is always negative. Which means anywhere the green is negative, it's kind of attracted to anywhere that there's a positive. So these guys will kind of hang out with this, and this will kind of hang out with that. And it's not a full-on chemical bond, but it's a strong magnetic attraction. Okay? And they're permanent. These were temporary. These are just every once in a while the cloud gets a little lopsided and they get attracted just a little bit. But these are permanent. These are always like this. They don't switch polarities ever. They're always like that. Okay? And as long as we're talking about kind of the same size molecules, dipole-dipole forces are much stronger than the temporary dipoles of dispersion forces are. Okay? And if we just specify this a little bit, we get something called hydrogen bonds. And it's most easily seen for us in water. It's when there's a couple unpaired electrons right here. Those can kind of bond with this hydrogen atom right here. Okay? So it's just a special version of the dipole-dipole forces. A hydrogen bond is a dipole-dipole attraction that occurs between molecules containing a hydrogen atom bonded to a small, highly electronegative atom with at least one lone electron pair. For a hydrogen bond to form, hydrogen is bonded to either fluorine, oxygen, or nitrogen. These atoms are electronegative enough to cause a large partial positive charge on the hydrogen atom, yet small enough that their lone pairs of electrons can come close to other hydrogen atoms. So what they're saying is that these are just the right molecules to where there's two little lone electrons here that are just strong enough to go meet this hydrogen and make this little bond right here. Okay? This is why water is a liquid at room temperature when comparable materials are gases at room temperature. We see that up here. So methane and ammonia are both pretty close to the same molar mass of water, yet they are very much gases at room temperature. Their boiling points are super low. The reason for that is because methane is not polar. So if it's not polar, it doesn't have those poles, the only thing keeping it together are the dispersion forces, which means it's only temporary, which means it's going to exist as a gas, because each molecule is going to be able to escape from the other one. There's nothing holding them together. Ammonia is polar, but you'll see there's a nitrogen in there, and nitrogen's not as strong as oxygen. So oxygen's a little better at keeping these hydrogen bonds in place. Nitrogen, not so much. So we see the boiling point is higher than methane, but still not anywhere close to water. So this too is not strong enough to stay a solid at room temperature, even though it's a comparable mass. Since they can't hold on to each other, they escape as a gas. Water we would expect to do the same thing, but because of these particular hydrogen bonds. Because of these hydrogen bonds, because it's oxygen, because oxygen's so electronegative, we see that it gets to stick together. And because it sticks together, it's a liquid at room temperature when these guys are gas at room temperature. And that's actually it for section 2, a pretty short section.